All right, here we have the Unit 1, Objective 1 notes on parent graphs and parent functions. So these notes are actually really long. There's like 34 examples. We're not going to do all those. We're going to skip around and kind of focus on the important things. So before we start graphing anything, well, we need to know, well, what type of graph is this going to produce? What type of graph is this going to produce, and that, and so on. So we need to know what our parent functions look like. Okay, so for our first example, y equals 2/3 times x. Well, what's that going to give us the graph of? Well, the answer is going to give us the graph of a line. If it's just x to the first power. X squared is going to give us something different. Absolute value of x is going to give us something different. And when x is the exponent, that gives us something different as well. Okay, so for our first example, a line. Well, what does the equation of a line look like? Now, there's different ways to write it, but the most useful form is point slope form, which looks like this. It's going to be y minus y1 equals m times x minus x1. Okay, so any line can be put in that form, and yeah, we can simplify that to point slope form, but this is how we want to leave it. This is the most useful form of an equation. Okay, and then this will work for any point. So if I have, squeeze this in here, any point, x1 comma y1. Okay, well, literally the x value of my point is just going to go right here in my equation. The y value of my point is going to go over there. Okay, so if I know my point and my slope, I can write the equation of any line. Okay, now we're going to skip to the bottom because, yeah, this is going to give us a line, this is going to give us a different line, but the most basic form of the equation of a line is going to look something like this, y equals x. Okay, so you might think, well, that doesn't look like this equation, but it really does if we just fill in a couple things that they left out here. For example, I could write this equation as y minus 0 equals 1 times x minus 0. Now, if you simplify that, what do you get? Well, you just get y equals x. So this is a line with a point at 0, comma 0 and a slope of 1. Now, if you know that, then you can draw your line. Plot the point 0, 0, go up 1 over 1, up 1 over 1, put a few points there, and you can draw your line. Okay. So anyways, this is just the simplest form of a line. This is what we call the parent function. Okay, now how do we graph a line? How do we graph a parabola? How do we graph an absolute value function? Well, you can graph anything, and remember this throughout the whole year. You can always graph anything by plotting points. Okay, so let's try it that way. If I just want to make a table of x and y values, then I can get enough points to produce a graph. Now, the bad thing about doing this is if you don't know what shape your graph is supposed to be, you might not pick some good points. Now, it's hard to mess up a line. We just need 2 points. But, parabola, if you only graph half of it, wouldn't really give you that U shape, for example. So this isn't always the most efficient way to do it, but you can always graph by plotting points. So let's plug in a few points. We'll plug in -2, -1, 0, 1, and 2. Okay, so if I stick in those points, well, what corresponding y values do we get? Well, if I stick in x is -2, I get y equals -2. So when x is -2, y is -2. When x is -1, y is -1. When x is 0, y equals 0, and y is 0. When x is 1, y is 1. When x is 2, y is 2. So those were pretty easy to get those points. Okay, next let's plot those points. So we got -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. Okay, and then we have here 5 points. Hopefully we know to graph a line we only need 2 points, but we have more than that, so that's fine. And we can now draw our line. And sorry, my handwriting probably won't get better throughout the year. But anyways, there is our first graph. So then that's the parent function of a line. And then anything we add to that equation is just going to change our line a little bit. Making this a -3 instead of a 1 is just going to change the slope. Making it a 2/3 is also going to change the slope. Okay, and we'll get to that in a minute. But then that's our first example is, drawing a line. Okay, next let's look at a quadratic function. Okay, so what is a quadratic function going to do? First of all, what makes it a quadratic function? Well, anytime we have x squared as the highest power of x, that's going to give us a quadratic function, okay, which is going to produce a parabola when we draw it. Okay, now, does every equation look like this? Well, no, obviously they can be a little bit different. So what does the equation of a parabola look like? Now, hopefully we remember from last year. Let's separate these here. But in general, a parabola's equation is going to look something like this. It's going to be y equals some a value times x minus some number, which we call h, parentheses squared, and plus some other number k. All right, so then that's the general form for a parabola. Now again, you might think, well, this doesn't look like that, or this at the bottom. Okay, and this is as simple as it can get. This is the parent function of a parabola. But really, it is in the same form as the other one, because what if I wrote this equation like this? What if I had it as y equals 1 times x minus 0 squared plus 0? Okay, well then, once I simplify, I get y equals x squared. So it's the same equation, they just didn't bother writing the zeros and the ones. Okay, and then how do we graph this thing? What is this going to look like? Well, again, if you forget, you can always graph by plotting points. So let's plot some points. Let's do the same points we did last time. So we're going to make a little table. We're going to stick in x's -2, -1, 0, 1, and 2. Now, these aren't always the best numbers to plug in, but we're plugging in a few negatives, a few positives, and then 0 sometimes is a special point as well. So this is a pretty good way to start. Anyways, if we plug in -2, so -2 squared would be +4, so then we get y is 4. We stick in x is -1. -1 squared is +1. We stick in x is 0. 0 squared is 0. Stick in x is +1. 1 squared is 1. And stick in x is +2. 2 squared is 4. So then we get these this list of points. All right, let's plot these points. So we got -2, 4. So left 2, up 4. 2, 4. At -1, 1. 0, 0. 1, 1. And 2, 4. Okay, and then once we plot those points, well, now if we connect the dots, we're going to see that we get this U shape here, which we call a parabola. Okay, so then that's the parent function of a parabola. Okay, and then everything we add to that graph is just going to change that a little bit. It might move it around, it might flip it upside down, might make it skinnier or wider, but that's what a basic parabola is going to look like. So again, we can graph by plotting points, or we'll talk about other ways as we progress. Okay. All right, and then next, well, what if we want to graph a linear absolute value function? Okay. Now again, they're saying that it's the equation of a linear absolute value function is y equals a times x. Just like these other ones were kind of simplified, but what do they look like in general? What are they always going to look like? Okay. Well, in general, our equation is going to look a lot like a parabola. A linear absolute value function is going to be something like this. Y equals some a value times the absolute value of x minus something, which we call h, and then plus k. So instead of the parentheses and the exponent, we've got absolute value bars. Okay, so it looks a lot like the equation of a quadratic equation. Okay, so here's an example of a linear absolute value equation, another one here, and then the most basic one is down here, just y equals the absolute value of x. Okay, so again, is that like our equation that we wrote down at the top? Well, sure it is. If we write it like this, I can say this is the same as y equals 1 times the absolute value of x minus 0 plus 0. Okay. So once we simplify this, we would get that. So really it's the same equation, they just didn't bother writing the ones and zeros again. Okay, well, what's this going to look like when we graph it? Well, if we're not sure, we can do it by plotting points. Let's plot the same points we did before. Okay, so if we stick in -2, -1, 0, 1, and 2, let's see, if I stick in x as -2, the absolute value of -2 is +2. The absolute value of -1 is +1. The absolute value of 0 is 0. The absolute value of +1 is +1. And the absolute value of 2 is 2. Okay, so now we get these points. Over 2, up 2, back 1, up 1, 0, 0, over 1, up 1, over 2, up 2. Okay, so we get those points. Kind of looks similar to that parabola, except it didn't go up as fast. And that's the main difference between the absolute value functions and the parabolas is the rate of change, the how quickly it's growing. Okay, the absolute value functions have a constant slope, which is going to give us this V shape here. Whereas the parabolas are growing faster and faster the higher you go. Okay, so then here are these first three basic functions, and we'll get to the exponentials in just a minute. But let's look at these three graphs. What do they have in common? Well, they all go through the point 0, 0. So on this first homework assignment, you're going to be dealing with pretty much everything going through the origin. Okay, if it's an absolute value function or parabola, then your vertex is going to be at 0, 0. And if it's a line, it's going to pass through the point 0, 0. Okay, and then how do we graph, different lines, quadratic equations, and linear absolute value functions? So let's do these top three examples, and then we'll get to the exponential functions. So let's see. If I'm not adding or subtracting anything to my equation, I know I got the point 0, 0 on there. And then, well, what does 2/3 represent? Well, that's our slope. So then a quick way to draw this line would just be to go up 2 over 3. And then once you have a second point, that's really all you need. I know the camera might be a little hard to see. Try to make it a little bit bigger. Then I can draw my line. If you want to put more points, you can. Going up 2 and right 3 is the same as going down 2 and left 3, just going backwards. So that gives me another point there. 3 points is more than enough. We can draw our line. Okay. How do we draw a parabola? Well, since it's not shifted anywhere, since I didn't add or subtract anything to my x's or at the end of my equation, I know my vertex is going to be at 0, 0. And then hopefully you remember from last year, lattice points. On our first parabola, since our a value was 1, well then I can go up 1 and over 1 and up whatever my a value is. In other words, we went over 1 and up 1. Now we can only do that once, because if I go over 1 and up 1 again, well, that point wasn't on my parabola. Okay. So anyways, up here, since my a value on this problem is 2, I can go over 1 and up 2. We call that a lattice point. Now remember, parabolas, the two halves of the parabola are mirror images of each other. So I can go over 1 and up 2 on the other side as well, giving me a third point. And once you have those 3 points, that's enough for a nice quick sketch of a parabola. Okay, so draw this. Parabola is going to be a little thinner than the first one we drew. It's going to be going up something like that. Not real pretty, but good enough. Okay, so as long as you have these 3 points labeled, then that's good. Okay, and then with the linear absolute value function, well, this one, since I didn't add or subtract anything to my equation, the vertex is also going to be at 0, 0, just like our first one. And then here, 2/3, much like the line, represents the slope of our absolute value function. Okay, so here we just need to know, is our v going to be opening up or opening down? Because we know it's going to look something like this. This a value just changes it a little bit. So since the a value is positive, it's opening up just like the parabola was. And we can literally just use this as the slope. We're going to go up 2 and over 3. That's going to be one part of our v. And then we can go up 2 and over 3 in the other direction. And then that gives us 3 points, which we can then use to graph. Now, if you want to, if you don't believe me, like, how are these points getting there? Well, if you're not sure, plug in x is what? 1, 2, 3. Plug in x is 3 to your equation and see what you get for y. Plug in x is -3 and see what you get for y. And you'll see that it's going to be those same points there. Okay. Now with the parabola, we can only use the lattice points once because the rate of change is different. But with the absolute value function, I can keep going up 2 over 3, up 2 over 3 as many times as I want and get as many points as I want. It's a little different for the parabolas, though. We can talk about that another time. Okay. So these first 3 functions are the parent functions of the linear, quadratic, and linear absolute value equations. And you can see we have the equations, what they're always going to look like up here. Now the last one, we saved exponential for last because it's a little different. These points all go through the origin. These graphs all have points that go through the origin. This one does not. Okay, but what is always on one of these functions? What point is always on one of these functions unless it's shifted or moved around? Well, the point 0, 1. Okay, now how am I getting that? Let's look at the parent function first. So the parent functions are all at the bottom. In general, it's going to be y equals some number raised to the power of x. Let's make it simple, and we're actually going to do the one that was at the top. Let's just change this to y equals 2 to the x. Okay, because it could be any number, but if we make it y equals 1 to the x, well, that's just going to give us a line, because 1 to any power is 1. And then if we use a number bigger than 2, well, it just grows too fast. So this is kind of what we call the parent function of an exponential graph. Okay, now, like with these other ones, is it always going to look exactly like this? Y equals some number raised to the x? Well, no, it could be a little bit different. In general, it's going to be y equals b raised to the x minus h. So we're sticking with the same letters as before to make it simple, and plus k. Okay. Hopefully it's clear that this is the exponent, so it's b raised to the x minus h, and then plus k at the end. Okay. In other words, h and k, just like with the parabolas and the absolute value functions, are going to shift our graph around. But if we don't have those, well, then it's always going to go through a certain point. And what point is that? Well, let's see. Let's plot some points here, just like we did before. So we'll do the same numbers, -2, -1, 0, 1, and 2. If I stick in x as -2, well, 2 raised to the -2 is 1/4. So we got to flip it and then square it. 2 raised to the -1 would be 1/2. 2 raised to the 0. Now, what's anything raised to the power of 0? It's 1. If you don't remember why that is, you can ask me. But that one's 1. I'm going to stick it over here so it's not getting mixed up with these fractions. 2 raised to the first power would be 2. 2 raised to the second power would be 4. So sorry, those are a little bit scattered, a little tight on space. Okay, but now we have some points. When x is -2, y is 1/4. So I can go back 2 and up 1/4. So I got to go up just a little tiny bit. When x is -1, I'm sorry, this should be positive 1/2. I don't know why I put a negative. Okay. When x is -1, y is 1/2. So just barely a little bit higher. And then when x is 0, my answer is going to be 1. When? Well, always, because again, any number raised to the power of 0 is 1. So rather than going through the origin, all these exponential functions are going to go through this point, 0, 1. Okay? And then what else do we have? Well, 2 to the first is 2. 2 to the second is 4. So we got a couple more points, and that's just going to grow faster and faster. Okay? And then that's going to give me a graph that looks something like this. So it's going to approach the x-axis, but it's never going to get there. Okay? Because think of it this way. 2 raised to what power is a negative number? Well, nothing, because if you make it a negative exponent, well, it's just going to flip it and make it a fraction. So it's going to get closer and closer to 0, but it's never quite going to reach there. So we call the x-axis an asymptote, which basically just means a boundary line. Okay? And then it just gets bigger and bigger as it goes up to the right. Okay? So then any exponential function is going to look pretty much like this. If you use a bigger number, like 3, it's just going to make it a little bit steeper. Because now when x is 1, y is 3. When x is 2, y is 9. So it grows a little bit faster. Okay? If you're struggling with any of this stuff, go to desmos.com and punch in some different equations. What happens when I make this a bigger number? What happens when I make it a fraction? What happens when I make my a value negative? You can play with that in Desmos a little bit. But I think for this front page, that's enough examples. So we'll stop there and we'll continue on to the second page in just a sec.